Hello, everyone. Welcome to the first webinar as part of our new 2021 Analytical Extravaganza. I'm Matthew Chaidez, Regional Sales Rep covering the Greater St. Louis area at Shimadzu Scientific Instruments. I'll be your moderator today. We will hear from Dr. Dipanjan Majumdar of Southern Illinois University, and his presentation topic is broadband optical spectroscopy of ultra-thin topological materials using our Shimadzu UV-3600 Plus. Before we start, I wanted to share a couple of notes for our viewers. The webinar console has a variety of items to help enhance your experience and interaction with us. In the screen, you'll see the following items. The slides will appear on the left-hand side. Directly under the slides, you will see a resource list with clickable links relevant to the material being presented today. On the top middle is a widget for questions and answers. Please submit your questions during the presentation through this widget, and we'll answer them during the Q&A session following the presentation. Just below the Q&A box are the moderator and speaker bios. You may expand the items here to learn more about us. On the right are survey questions that you may fill out anytime during or after the presentation. Finally, at the bottom pane are the icons to bring up all these widgets in case they're minimized or hidden. All right, without further ado, let's get started. Again, if you're just joining us, I'm Matthew Chaidez, your moderator. Today we'll be hearing from Dr. Dipanjan Majumdar, and his topic is broadband optical spectroscopy of ultra-thin topological materials using our Shimadzu UV-3600 Plus. Dr. Majumdar and his researchers are interested in the growth of new materials and investigate physical properties affected by size, chemical doping, interface, heterostructure, and external tuning parameters such as light, magnetic field, and so on. They are particularly interested in understanding the optical and dielectric properties of novel electronic materials that are fabricated in their lab in thin film form. Since the discovery of graphene, transition metal dichalcogenides, or TMDs, have emerged as one of the most exciting systems to investigate properties at the nanoscale. In their lab, they have developed few-layer, large-area MOS2 thin films using a PVD-CVD growth process that can produce films with tunable properties. For this talk, he will specifically focus on their broadband dielectric properties measured using our Shimadzu UV-3600 Plus. Next, he will discuss their work on the influence finite-size and topological insulator Bi2 Se3 thin films. Through a combination of quantum confinement and Burstein-Moss effect, they have discovered a large optical blue shift in Bi2 Se3 as it approaches the 2D limit. Now, I will hand it over to Dr. Dipanjan Majumdar.
Hello. My name is Dipanjan Majumdar from Southern Illinois University at Carbondale. First of all, I would like to thank Shimadzu Corporation for organizing this talk, and Matt in particular for inviting me. Today I will share some experimental data on the optical and dielectric properties of novel electronic materials that we synthesize in our lab in thin film form. The data was acquired using the Shimadzu UV-3600 Plus optical spectrometer. It is one of the first major instrumentation that I purchased for my then new lab at SIUC. Since then, it has been a workhorse and used it to publish 4 or 5 papers to date, and hopefully many more to come. As I go along, I will acknowledge some of the students who were involved. At the end of the talk, I would be happy to take in some questions. So let us get started. My research area is experimental condensed matter physics and materials physics. This is an interdisciplinary research area involving physics, chemistry, material science, and engineering. Over the past 20 years or so, this area has seen the discovery of several new material properties. These materials are not necessarily chemically new, but they were shown to have some extraordinary physical properties, be it electrical, mechanical, or optical, and so on. Some of you are familiar with graphene, which is a single layer of graphite, which is the material pencils are made of. Not very long ago, it was thought that it is impossible to isolate a single layer of graphite or graphene as we know it now. However, a single graphene layer was isolated sometime around 2004 and shown to possess extraordinary electrical properties and mechanical strength. And it was not surprising that the discoverers of graphene were awarded the Nobel Prize in Physics in 2010. Like graphene, there are also other layered materials. That means materials which can be isolated into single layer forms or 2 layers or 3 layers, like it's shown in the figure. So there, like graphene, there are some layered materials which are classified as transition metal dichalcogenides, or TMDs in short form. Hexagonal boron nitride is another example. So these materials also show several of the properties that graphene has shown while overcoming some of its shortcomings. I would begin talking about our work on layered materials, specifically molybdenum disulfide. I would also put in this list, even though this is far from my research area, that in 2008 or so, superconductivity was observed in iron-based materials. And this is also considered a major breakthrough because superconductors are not usually associated with magnetic materials. They are associated with non-magnetic materials such as copper and so on. But not iron. And iron, of course, everybody knows is the quintessential magnet. So in effect, this means that superconductivity and magnetism can coexist. Previously, it was thought that they could not coexist together. So I just wanted to mention that in this list of new materials or discoveries in the area of physics and condensed matter physics. Also at around 2008, 2009, another material family also gained tremendous interest, which are called topological materials. I would actually explain what topological materials are in some detail during this talk and provide some of the work that we've been involved with on topological materials. The theorists who predicted the existence of topological systems in the 1970s and 80s actually received the 2016 Physics Nobel Prize. As I mentioned, isolating the single layer of graphene-like materials turned out to be a very interesting proposition, as it is accompanied by significant changes in their physical property. Here I will talk specifically about MOS2, which is one of the TMD material. In the left image, I'm showing 3 layers of MOS2. The distance between the layers is about 1 angstrom, give or take. In the middle figure, middle region, I'm showing 2 figures. Now, excuse me if I'm being a little technical here, but you essentially see a bunch of lines, right, that look like spaghetti in each of the figures. The diagrams are called the electronic band structure diagrams. So don't worry about what these lines mean, only the fact that they are bunched up into what we call bands. And you see 2 bands, right, for each of these figures, in each of these figures. And there is a gap between the bands. And this gap value is one of the defining properties of a semiconductor called the band gap, and denoted by the Greek letter delta here. Now, MOS2 is not a new material, actually. It is very popularly used as a lubricant because the layers can slide very easily, just like graphene, and it has also some other practical applications and used in the industry. In the bulk form, which is when you have hundreds and hundreds of layers put together, the band gap is known to be around 1.2 eV, 1.3, which is in the near infrared region. It was first observed in 2010 that when you isolate a single MOS2 layer, the band gap changes from 1.2 eV to about 1.9 eV, which is just about the red part of the visible spectrum. As the figure on the right shows, 2-layer is about 1.6 eV band gap, 3-layer is about 1.4, and so on. And again, you might say that this change is small. You're changing from 0.5, 0.6 eV, maybe 0.7. Now in physics, this is a huge change. It's just like saying the height of a person changes from 6 feet to 10 feet. Now, that does not happen normally or ever to a single person. So it's, that is as unusual as that. So such changes are driven by a process called quantum confinement, and we don't have to worry about that. So this is just one of the things that's happening when you go from a bulk MOS2 to a single layer MOS2. There are also other things that's happen. The gap character, which is something denoted by these arrows in the middle figures, it changes from an indirect gap to a direct gap. Now, as you can see in the single layer MOS2, the arrow is vertical, so that's a direct gap system. And for the bulk MOS2 band structure, the arrow is pointing to the left. That is an indirect band gap system. Now we know that the direct band gap systems are preferred for application as they absorb light very efficiently. Indirect band gap systems are weak absorbers. Therefore, so the take-home message is that a single layer MOS2 is a very, very strong photodetector compared to the bulk, even though it is, only a single layer, right? We know that the absorption property increases with thickness. So even if you normalize that factor out, so per layer, the single layer has more strength than the bulk MOS2. So now this is huge because now you can think about applying MOS2 for some nano devices application, right? And there are also other interesting things that's going on with MOS2, and I'll talk about the excitonic feature of these systems in about a few slides. All in all, I hope that I've pointed out a few things that are very, very interesting about this material. So we are done with the introduction part of the MOS2 material. Now I want to explain what projects I've been involved with in my lab in the last 4 or 5 years, and that really has to do with the growth part of this material. Now, as I was mentioning, when graphene and other TMD materials, they were discovered not by any thin film growth method. They were discovered by essentially what is called the Scotch tape method. That essentially what you do is you take a Scotch tape and peel away layers of the material. So when you peel off, you take a single crystal, put a Scotch tape on it, and you peel out as much material as you can, and then hope for the best, literally, because whatever you peel out could be 10 layers, could be 20, but could be 1, 2, or 3. And then you individually look into all these flakes that you gather, and you make sure that you have the thinnest layer. Then you go to an AFM and measure the thickness. If the thickness comes out to be roughly, like I was saying, 0.7, 0.8 layers, then you got a single layer. If you got a 1.4, you got double layers. So that's how the layers were found out to be either a single or a bi or a 3-layer or a 4-layer. Now that does not sound to me very, very productive if you want to do large-scale applications. If I take this idea to the industry, this will not fly at all. So the growth method is really a stumbling block for practical applications of these materials. Devices require large area heterostructures. That is not possible with this Scotch tape method, or what also another word for this is called exfoliation method. So how to develop large-scale MOS2 and TMD materials is actually a very, very relevant research problem, and that's where I jumped in. So in my lab, I had this magnetron sputtering thin film growth facility. Some of you might be familiar with magnetron sputtering. You take a target, you bombard it with highly energetic argon ions and sputter away some of the material, and they diffuse and deposit on a substrate which is lying a few inches away, a couple of inches or 3 inches away. And if you have the sample at a high temperature, they can grow in epitaxially or in single crystal form, and also you can layer it with other materials. So magnetron sputtering is an industry standard. It's also used in the optical industry when you coat mirrors and glasses, right? So sputtering is the way to grow thin films, large area thin films. So when I started this project, I thought, hey, why not take an MOS2 composite target that is commercially available and sputter a film out of it and look at the optical properties. That could be a good start. So I got a student, Hassana, who was my first PhD graduate student. So he was interested to grow the material. Then I got another student, Asma, who was interested in looking at the optical properties. And by this time, I had purchased the optical spectrometer from Shimadzu, which allowed me to measure broadband optical properties going from 0.375 eV to 6.2 eV. And most of the time, most of the data that I'll be showing you today is essentially optical transmittance data and analyzing the absorption and dielectric properties from the transmissions data. So this transmittance data or transmission data is over this broadband region, not necessarily all from 0.375 in the case of MOS2. Since the band gap is really around 1.2 to 1.9, we did not really need to go much below 1 eV. So I'm going to restrict our MOS2 data from about 1 eV to 6 eV. Whereas in the later project I'm going to show, when we discuss bismuth selenide, there we had to go to 0.375 eV because the band gap was much lower. So this is the framework. So I'm going to show you next are some methods of growth, how we optimize the growth, and how we characterize this growth process using our optical spectrometer. So this is our first attempt to grow MOS2. That's why I call it version 1. Here we just took a composite MOS2 target, sputtered the film, and we annealed the sample at around 300 to 400 degrees and looked up the optical properties, electrical property, and the structural property, the crystal structure. So first assessment we did was the surface, which is shown using AFM, atomic force microscopy. So it looked really smooth. We also did X-ray diffraction. We did find the X-ray diffraction peak for MOS2. So our first check was really good. That means, oh, we have an MOS2 film, which is large area, right? So that is already a stumbling block. So we looks like we have done something in that direction that could be useful. And that was good enough, honestly, to publish the data in 2017. So this is Hassana's paper. Asma was the second author in this paper. And but then slowly we realized that there were also issues with this growth method, as I will explain next. So as I said, we did observe X-ray diffraction peaks, but the X-ray diffraction peaks were broad. They were not as sharp as they can be. I'm not showing the X-ray diffraction peak here. I'm showing on the left-hand side, I'm showing the Raman data, which is characteristic to MOS2. We see two Raman modes here, called the E mode and the A mode. So these peaks, again, are known for MOS2, so we found that. But their peaks were broad compared to the single crystal exfoliated sample data. And the other part, of course, I did not quite mention here again, is that our growth method was really optimized to grow 3 to 4 layers, not exactly 1 or 2 layers, because it's a very large area, and it's across 1 inch substrate. So we were not able to confirm that we were growing a monolayer across 1 inch substrate, but we were able to confirm that it is 3 to 4 layers through all this characterization, particularly Raman, where we do a lot of spot checking. So we found the same E peak and the A peak over the entire sample. So this is actually a 3 to 4 layer sample, and that we confirmed from Raman, not a 3 layer or a 1 layer sample, 2 layer or a 1 layer sample. But that was itself quite challenging, and that itself got a lot of mention because, again, as I said, it's still an outstanding problem to grow a uniform single layer MOS2 across such a large area substrate. So coming back to the issues with MOS2, as I was saying, that the Raman modes were particularly broad, and also when we put this sample under through our Shimadzu spectrometer, we were expecting that around 2 eV, which is slightly above the band gap, a doublet feature, and these are called excitonic features. So we were expecting this peak around 2 eV, there would be 2 sharp peaks. Instead, we found 1 broad peak. Now these peaks, the physics of this are a little bit hard to explain, but these are excitons. So again, like the band structure we were talking about, the optical transitions are from an unoccupied band to an occupied band. So the bands on the top, those are unoccupied band. The bands at the bottom, the 2 bands at the bottom, are occupied bands. So, and if you do the math, there are at least a couple of transitions that we should be seeing at around 2 eV, and those are associated to what is called excitons, which are electron-hole pairs. So anyway, so as far as characterization is concerned, we were hoping to see 2 peaks here, but instead we were looking at a single broad peak, which again pointed to disorder. Now, what kind of disorder could we have? So there were lots of speculation that, that might be that our MOS2 sputtering process is causing lots of sulfur deficiencies. So we don't have all the sulfur that we need to make a stoichiometric MOS2 film. So it is sulfur deficient MOS2. So that was our hypothesis. And again, we used the Shimadzu spectrometer to check these hypotheses. So what we did next was is what is called we adopted a sulfurization step after the thin film growth. What is sulfurization? Well, we just took some sulfur powder, heated it up, and had it flow over the MOS2 thin film, which is kept at a very high temperature, 700 degrees in this case. So this process is called sulfurization. That means you essentially, surround the MOS2 film in a sulfur-rich environment and hope that all the missing sulfur is replenished. Okay. And if it gets replenished, we should see immediate verification through our optical characterization. So that was the hypothesis. And sure enough, we see that. So the data on the left shows the data before sulfurization. Again, this is a 3 to 4 layer MOS2. And the data to the right is the optical data, absorption data after sulfurization. And you can clearly see that this broad peak at 2 eV is now has now changed to 2 sharp peaks, and these are the excitonic peaks that we are looking for. So immediately it told us that that the sulfurization step is working, and it produces these clear excitonic peaks that we expect to see for MOS2. That was basically the basis of more follow-up work that I'm going to talk next. So what we did next was we had established this large area MOS2 films with clear excitonic peaks, and also the other optical features, as you can see, marked by the C and the D exciton. So all in all, this was already reported in the literature for single layer, 2-layer, and 3 to 4 layer. So this is a 4-layer MOS2. This was reported for these exfoliated samples produced by Scotch tape, but they were not reported for these thin film samples grown by the method that we have chosen. So we immediately thought of the idea of extending our data to beyond these A, B, C, D excitons. But that meant that we have to use a broadband spectrometer rather than this 1 to 3 EV spectrometer, because a lot of this data that is published in the literature were obtained using ellipsometry. Ellipsometry is another technique, but most of the commercial ellipsometers, they are limited to about 3.2 EV. But because we had the Shimadzu spectrometer, which would go to 6 EV, we immediately thought of a project of measuring the broadband optical spectroscopy of the 4-layer MOS2. And by that time, we were also doing a significant amount of band structure calculations, like I was showing all the spaghetti lines. Again, lots of vertical lines that you can see here. And again, that lines helps us, those lines help us to assign the optical transitions. We have assigned the A transition, the B transition, the C, and the D here. These are all direct transitions, some close to the K point, some close to the M point. But then we proceeded, hey, let's do the broadband spectra. And once we did that, we saw this nice extra broad peak at around 4 and 4.5 EV. Now this is again new in the sense that for 4-layer MOS2, this data was not known in the literature. So this is valuable stuff. But keep in mind, this is 2018 when we got this data actually. And MOS2 single layer was discovered in 2010. So even after 8 years, as easy it might sound, people have not looked into the broadband properties of few layer MOS2, 3 to 4 layer MOS2 in the detail that we are showing here, because most of the applications are, or the interest is at the A and B exciton rather than the high energy transitions, which I'm showing here. So this was already a novel enough project for us, and we were in a position because we had the films available to us. So immediately we analyzed these E exciton, and we could assign this peak to direct transitions at around the gamma point, as shown here. So you can see that the energy difference matches very well. And as I was saying, direct transitions are very strong processes. So an E peak, you can see it's very strong, it's very broad. Again, I'm not showing here the band gap. This is the dielectric property. This is the imaginary part of the dielectric constant. You can see even at 4 EV, the dielectric constant is above 10. And the dielectric constant can go as high as 20, 25 for MOS2 around the C and the D exciton. So these are very, very strong light absorbing materials. Even for 4 layer, a single layer is very strong, like I was saying before, because of direct transitions. These are also other direct transition processes, and these are also very strong. And that is one of the new things we're learning about this material, that even for a 4 layer, to observe such a high dielectric constant is unusual. And that is one of the reasons we're trying to find out what makes these materials special. And now we know that there are things like called band nesting effect, which I'm not going to go into the details. Essentially, it comes from the band structure of this material. When the bands, the conduction band and the valence band are parallel, you do have very strong optical absorption processes. So anyway, so that's going to be probably mentioned more in the paper that we're writing, and I think I distributed that with Matt. It's an unpublished work, so this is part of that work. So again, long story short, we assign this E transition, interband transition, to our direct transitions at the gamma point of the band structure. So this is what's going to the paper, but it may be too technical, but more or less we have used the broadband properties that's offered by our spectrometer here. And here I'm showing the real and the imaginary part of the dielectric constant. On the left-hand panel, the top and the bottom, I'm showing the experimental data that is obtained using transmittance spectroscopy, using our spectrometer. And on the right, I'm showing the first principles calculation that is used with a technique called density functional theory. This is a theory that's employed by physicists and chemists and material scientists to calculate the electronic structure. Now, what we are doing here is really a direct comparison of the experimental data to the theory data. Now, you can see there are lots of common features, and there are some differences too. But we think this is as good as it gets. Particularly, the dielectric constant values match up very well for different layers, right? And all the big features are captured, the C and the D. The AB exciton peaks are not captured in theory because this theory does not include those features. And I'm not going to detail why it does not. You can see in theory you have a broad peak instead of this doublet structure. But the E transition is picked up. That means that E transitions are not excitons according to us. And also, we also see pretty good reasonable agreement in the scaling behavior. What do you mean by that? That means that the dielectric constant of 18 layers is higher than the dielectric constant of 4 and 5 layers. Sometimes, as trivial as it might sound, it is not very easy to show it because of strong interference from substrate. So we have to carefully eliminate the substrate effect here to show the right scaling behavior. And that took Asma, who is the first author of this work that will be published soon. It took her 1 year or so to come up with a systematic process to analyze these few layer materials, right? So because we were seeing this artifact that a single layer had much higher dielectric constant than 4 layer, which means that you're reducing the material, the dielectric constant keeps on increasing. That is unphysical. That's the opposite trend we expect. And that was pretty much due to what we now know is from the substrate. So once you eliminate the substrate and properly normalize all the data, you would be seeing the right scaling behavior as predicted by theory. So this is pretty much our best agreement. And as I was mentioning, having done this for a few years now, this is as good as it gets. So we are happy with where we are on this project. We are finishing up this paper, and hopefully it will be published sometime this year, very soon. So to summarize our MOS2 project, what we have shown here is that we developed a hybrid process to grow these materials in large area form, where we are taking the good part of sputtering, and also we are doing a second step using a process called sulfurization, and this is sometimes called the chemical vapor deposition process. So it's a hybrid CVD PVD, and then we analyzed the broadband optical properties of MOS2 and found many interesting transitions. One of them, which we think is not reported in the literature, as far as few layer MOS2 goes, and we have assigned this transition also. So thank you for listening to the first part of the talk. Now I'm going to transition to the next part of my talk, which is going to be on topological insulator materials. So here I'm going to talk about the optical properties of few layer bismuth selenide topological insulator thin films. Again, a few layer, that's the common theme with MOS2. I'm talking about 2, 3, 4, 5 layers, not a single layer. And again, focusing on the optical properties. Here I'm going to be specifically talking about the band gap of bismuth selenide. Now this is going to utilize the lower end of Shimadzu UV-3600 Plus, the lower energy end, the near infrared and the mid infrared part. I want to quickly recap or mention what we're trying to do here in this set of measurements. So here we are trying to measure the band gap of these topological insulator materials. I'm showing on the right hand side a simple schematic of a semiconductor. So this is a simplified version of all the spaghetti lines I was showing earlier. You can see that the band structure is divided into a conduction band, which is given by the upper parabola. And we have a lower parabola, which is the valence band. So all the electrons are, all the valence band states are occupied and the conduction band states are unoccupied, and optical transitions are between the valence band and the conduction band. And of course, these two bands are separated by the band gap, which we have already discussed. There's only one more thing that we need to track here is something called the Fermi level. The Fermi level is the highest occupied electronic level here. And so since in a semiconductor, the valence band is completely occupied, the Fermi level is just on top of the valence band. And the conduction band is empty, as I told. As opposed to a metal, on the left-hand side, a metal, you can see the Fermi level is intersecting the lower band, right? And that is the hallmark of a metal. Whereas in an insulator, the band is what, as we say, is completely filled or empty, right? So the valence band is completely filled, or the conduction band, which is completely empty. Whereas in a metal, the bands are partially filled and partially empty, like you see here. So this is the thing that you have to keep in mind as we move forward. So what is a topological insulator? Well, these are insulator materials with a metallic surface state. Okay, so it's insulator in the interior, but the surface is a metal. And you can see that this cartoon picture shows the band structure of a topological insulator. You see really two extra straight lines here compared to the figure I was showing earlier. And that is the signature of the metallic surface state. What is unique about this metallic surface state is that they are immune to disorder. They cannot be destroyed very easily, and they are protected through the topology of the material. And again, I'm not going to go into the details what I mean by that, but essentially fancy math. This topology is a branch of mathematics. It ensures that the surface states which are created in this material are not destroyed very easily. So they're chemically robust, immune to disorder, and that clearly implies that they can be used for technological applications in a very nice way, because people are thinking of making quantum computers with it, fault-tolerant devices with it, and lots of applications which will lead to low energy applications. So none of these, hypotheses would be exciting unless experimentally it's proven. So this is experimental data I'm showing on bismuth selenide, and this was only shown in about 2008, as I was mentioning before. So bismuth selenide again is not a new material. This material has been known for a long time. This is actually popular thermoelectric material. But in 2008, the group of Zahid Hassan and Bob Kawa grew the single crystal. Zahid Hassan's group measured this bismuth selenide material using a technique called angle resolved photoemission spectroscopy. And the data is shown here. You can see these lines on the left-hand side of the image And that really conforms to these cartoon straight lines that I was talking about, which are the signature of the surface states. So this is the experimental proof. So this technique is called ARPES. So using this ARPES method, it was proven that indeed we have a signature of topological materials, measure these band structures, and look at the existence of surface states. And ARPES turns out to be the best method to do that. So I'm not going to go into any more details of what topological insulators are. I'm going to switch to, again, what we are interested in primarily. So what we are interested in is what is related to the finite size effect of bismuth selenide thin films. So again, I'm showing a bunch of ARPES data in the panel. You can see the one on the left is a 2 quintuple layer sample. That means it's a 2-layer bismuth selenide. Now, bismuth selenide, technically when I mean 2 layers, this is a very complicated material. You have 2 bismuth atoms and 3 selenium atoms. So each layer is called a quintuple layer, which means it has a layer of 2 layers of bismuth and 3 layers of selenium. That makes 1 quintuple layer. So 2 quintuple layer is essentially many layers, so 10 layers of atoms, but it's 2 unique, 2 complete chemical cells of bismuth selenide. Okay, so you have 2, 3, 4, 2, 3, 5, and 6. You can see the 6 quintuple layer bismuth selenide clearly shows the surface states, and the surface states are touching each other. You can see that those 2 straight lines are crossing each other. As you go below 5, when you go to 3, you can see those surface states are no longer touching each other. There is a gap in the surface states also. Okay, when you go to 2, this gap is even stronger, right? So that's kind of what's happening, since when you go from a 6 quintuple layer, which is kind of a 6-layer bismuth selenide, 6-layer bismuth selenide is showing basically like the bulk structure, right? The bulk electronic structure. When you go to 3 and 2, the surface states also develop a gap. And also you can see another thing that's happening. Of course, we are zooming in to the surface states. We are not showing the bulk, but the bulk states are just above and below those surface straight lines, the surface states, right? So they are also getting pushed up and below. And you can see this bright yellow feature. Those are corresponding to the bulk states. You can see that for the valence band, the bulk states are getting pushed lower, and for the conduction band, the bulk states are getting pushed higher. So the bulk gap is also changing. And this kind of gave us the idea is that can we measure this through optical spectroscopy? Okay, so a lot of the data that we have out there is really looking at these ARPES measurements, right? Looking at the surface states. So when we looked into this problem, he said, our optical spectrometer is really sensitive to the bulk states. They're not necessarily sensitive to the surface states directly, because the surface states are hard to observe through a direct optical spectroscopy measurement, but the bulk states are easy to observe. So we thought, hey, can we measure this gap change due to the finite size effect in bismuth selenide thin films? So how we are measuring the band gap, no light is absorbed when, of course, the energy of our light is less than the band gap. And as soon as we apply a high energy light, which exceeds the band gap, we see some optical transitions, which results in absorption. And that will, if properly analyzed, we should be able to extract the band gap information. So this is standard information, again, going back to what we are talking about, what we were talking about earlier. So it should be clear at this point. So the first thing that we did was to measure the transmission of several bismuth selenide thin films these were also fabricated using the magnetron sputtering method that I was talking about earlier. So I'm not going to go into details. It's very similar to MOS2. We take a composite target, we sputter, anneal the sample, look at the optical absorption. Okay, so I'm looking at the transmission data of a 2 quintuple layered samples. So unlike MOS2, we had better luck in depositing a 2 quintuple layer bismuth selenide. So this is about 2 nanometers, right? So, and I'm kind of showing you a couple of data here. The sample on the left, we left the bismuth selenide uncapped. That means there was no protective layer on the bismuth selenide layer. And on the right, we protected the layer with a thin boron nitride insulator. Now, boron nitride is basically wide band gap insulator, so it's transparent to the light. So we were not worrying about absorption of the boron nitride layer. The reason we did this was to protect the bismuth selenide layer from getting oxidized, because there's always, we are measuring the changes of a very thin film. If the film gets oxidized, we are not really talking about bismuth selenide anymore, right? So we have some other film. So, and this was a genuine concern, so we did the test. What we found is the uncapped films do show some changes, right? So you can see the 2 data here. In overlapped on top of each other practically. So one taken 6 minutes after deposition and the other taken 4 hours after deposition. So 6 minutes is the time which literally we needed to bring the sample from the deposition chamber to the optical spectrometer. And in the case of uncapped sample, we saw that there is a small change. In the capped sample, there is virtually no change, and that is exactly the result we wanted to see. That means if we analyze the capped sample, we would be sure there is no effect of surface oxidation. And so we proceeded to analyze both these capped and uncapped samples. Here is probably the most important result. You can see that I'm plotting the optical absorption spectra of a 2 quintuple layer and a 6 quintuple layer bismuth selenide film. Okay, 2 and 6. Clearly, you can see that the onset of optical transition in 2 quintuple layer sample is to the right of the 6 quintuple layer sample. Okay, so the absorption spectra starts a little bit to the right, so it's blue shifted as we reduce the thickness. Okay, and we can go ahead and analyze the optical band gap using the direct gap analysis. Sometimes these are called the TOC plot. And again, this is straight up a Beer's law, right? So we are doing an absorption analysis using the transmittance data and knowing the thickness. The thicknesses were calibrated using X-ray reflectivity method. Again, you can clearly see that the optical band gap of a 6 quintuple layer sample is about 0.5 eV, whereas the band gap of a 2 quintuple layer is about 0.8 eV. Okay, so that's the inference from here. And then we essentially plotted all sorts of samples that we had, both the capped and uncapped, and plotted the band gap estimation as a function of the layer. And you can see a very nice trend irrespective of the capping and uncapping. We can clearly see that as we reduce the thickness, the band gap is increasing, right? It starts off at around 0.5, like we were showing for 6 layer, and that permeates even till as high as 16 layer. But as we go below 6, 4, 3, 2, 2 is almost 0.8 EV or higher, right? So this was a new thing that we were seeing. So clearly we see a strong optical blue shift in few layer bismuth selenide. Okay, so this is kind of the summary, right? So bulk bismuth selenide, I did not mention that. The bulk bismuth selenide has a band gap of 0.3 eV. Now in all our samples, as high as 30 quintuple layer, we saw the band gap go as low as 0.45. Okay. 6 quintuple layer, as I was showing earlier, the band gap is around 0.5 and 2 is 0.8. So we do see two things happening here. Okay. So one is, why don't we see a 30 quintuple layer or even a 10 quintuple layer show a 0.3 EV gap? So that is the first question. So are we overestimating the gap because of some instrumentation problem or an artifact or some systematic error, or is it real? So that was the first question. Okay, so but we came to the conclusion, no, this is not a systematic error. This is another effect that's happening in our films called the Burstein-Moss effect, and I'm going to explain very quickly what that is in a bit. And the second effect is what we are looking at is the finite size effect, right? That's we were expecting in bismuth selenide. So as you go from 6 to 2, the band gap is going to changing from 0.5 to 0.8. Again, small change, but like MOS2, 0.5 to 0.8. This should be seen a 60% jump, right? Again, the height of a person does not change by 60% abruptly. So this is a huge change, and that is due to the finite size effect. So combined Burstein-Moss and finite size is giving us both these changes. So what is Burstein-Moss effect? Again, so what is a Burstein-Moss effect? Again, it's observed in semiconductors which have a lot of carriers, and this is one of the features of bismuth selenide. Even though we call it a semiconductor, the number of carriers in bismuth selenide is really higher than normal semiconductors. It's almost approaching that of a metal. So, so what happens is that the valence band is completely full, and some of the extra carrier, they go up and occupy the conduction band. So once that happens, the optical processes are a little bit now complicated. Now in bismuth selenide, what we think is happening is that the valence band is occupied and the lower part of the conduction band is also occupied. And that's why it's called a degenerate semiconductor. So now when an electron from the valence band has to jump to the conduction band, it cannot jump into one of the occupied states. It can jump only to the unoccupied state. So it has to jump all the way over the Fermi level in the degenerate semiconductor. So you can see there is an apparent increase in the band gap. Okay, so instead of measuring 0.3 EV that we expect for a non-degenerate semiconductor, we see that now the band gap has apparently increased, and it has increased by the amount the conduction band is occupied, right? And I'm showing you the thickness, the concentration numbers that we extracted from our transport measurements, and these are really degenerate semiconductors as we are hypothesizing, and this is something that even other groups have pointed out. So that's what's happening. So we see an apparent increase in the band gap due to the Burstein-Moss because the conduction band is partially occupied. So it is kind of a quasi-metal, which is more like a metal than a semiconductor in the strict sense. Plus, we observe this finite size effect that we are really hoping to uncover here. So of course, like these are again band structure data, like I was showing. These are again back to spaghetti lines, very complicated. This is obtained through DFT. This is the band structure shown by another group, and our data agrees with that. You can see that the gap. So the light red lines, those are the surface states. You can see like when you go from a 4 quintuple layer on the right to 2 quintuple layer, the difference between the surface states open up a gap, and the bulk bands move away from each other, right? So you can see that like I'm drawing this dashed line. So that's the difference we are picking up. It's a small difference, about 0.2, 0.3 EV due to the finite size. Like I told before, we are not sensitive to the surface state. So the band shown by this blue arrow, we are not sensitive to that, but we are sensitive to the band above and the band below that. and that band gap is changing, and that's what we are measuring here. Okay. Later on, we actually concurred this observation using transport also. We saw that the resistivity of this material also increased as we reduce the thickness. Now, when the resistivity increases, we say it's getting more insulating. More insulating means a higher band gap. That's what we are plotting here, trying to show that resistivity is exponentially dependent on the band gap. And that seems to corroborate with this theory, with this observation that the gaps are increasing as you reduce the thickness. So all in all, this work was done by Yuvraj Sapkota. I probably should have mentioned his name earlier than I did. So he was the sole graduate student who did the thin film growth and measured the optical property and the transport property. So thanks to him, and there are a couple of papers that's already being shown here. So what we learned here is that we observe a strong optical blue shift in bismuth selenide. This is similar to MOS2 actually. So this is coming back to the how does the band gap change when you reduce the thickness. So we kind of came back to the same idea for bismuth selenide, even though bismuth selenide is not usually seen as that kind of a material, right? It is more, topological insulators have their own, exotic properties that people are after. So we kind of found kind of a simple result, like a semiconductor result, like TMD kind of result here. So again, we are seeing the realization of two effects, the Burstein-Moss and the finite-size effect, which is leading to the increase in the band gap of the material. And our results seems to be verified using transport measurements also, right? So with this, I conclude my talk, and I'll be happy to take questions and after this webinar is over. And yeah, so please feel free to shoot some questions and I'll be happy to talk about it. So thank you for your attention.
All right, let's thank Dr. Dipanjan Mazumdar for such an exciting presentation. Again, under the resource list, you can find more information about our analytical solution. If you've not had a chance, please fill out the survey questions on the right-hand side to provide feedback and request additional information. At this time, we will begin our Q&A session. Thank you to the audience for attending and sending questions. And we do have a time for a few questions, and I will moderate them as they come in. Dipanjan, thank you very much. So the first question that I have from the audience is, it appears that you are working mainly with solid samples. What kind of accessories do you use with the UV, and what are some of the challenges compared against transmittant measurements of liquid and cuvettes?
Hey Matt, thanks for organizing this again, and thanks everybody for your patience in listening through the talk. So as far as the questions concerned, yeah, so one of the things that we are doing is actually our thin film samples. We spend a lot of time to fabricate it to make sure they are very much compatible with our measurement. So we minimize, so that's why we grow them in a large area, and that turns out to be sometimes difficult to do. So because of the prior experience and everything, when we got this instrumentation, we made sure we got some of the apertures, because sometimes we do not get a nice uniform film over the entire area. That's always a concern. So when you do transmittance measurement, is the light seeing a very uniformly thick film? And so when we have that concern, we try to use apertures, which I think I required. The other part is the substrate turns out to be very important for us. And that is something, suppose we are using quartz here, the quartz substrates, and also like boron nitride cap, it was made specifically for this measurement, for this transmittance measurements. But very often we have to use very absorbing substrates like silicon. So then transmittance becomes very challenging. One way of doing those kind of measurements is actually to thin down the substrate. And, so we have a polishing accessory. So we don't want a thick substrate. We sometimes have to thin down the substrate to about 100 microns or less, which itself is pretty challenging because these films are, as I said, these layered films are very flaky. They flake off very easily. That's how, you do the Scotch tape thing. So polishing the substrate also becomes a bad idea. So we could not do this for bismuth selenide. So that's why we were pretty much restricted on what kind of substrates we could use. To circumvent that, I got another accessory, which is not transmittance, but we do reflectance measurements. And Matt, you would remember I got this specific accessory so that we can do reflectance, because in principle, we can also get the absorption spectra from the reflectance data. So combining transmittance with reflectance, we try to make sure that, we cover the entire bandwidth. We cover, because these solid state films, as you pointed out, these features are very broad. We do not see very sharp atomic peaks. So we have to measure across a large bandwidth. And that is really the reason why I chose Shimadzu. They give me the largest possible bandwidth. And one thing I do want to mention that I was really surprised that the sensitivity you guys have at the middle infrared, near infrared side, because for bismuth selenide, that was literally the first project we did. My prior experience doing the middle infrared was, we'll see a lot of water lines and all these things, but you guys did a very good job. We didn't see much of that. We did do some smoothing of curves because of, and so some post-processing was done when we were merging all the data and stuff, but all in all, we didn't have to do a whole lot. So coming back to probably the broader question also compared to liquids. Now, the one good thing about thin films is that we don't see a lot of scattering of light because they are very low roughness. So we didn't have to worry about that. So the transmittance measurements, we're not losing any light as such. The only light we are losing is the reflection at the substrate and at the film substrate interface. So in a way, we avoided all those issues of that you face in liquid. So together with reflectance, I think we are good with all the accessories.
Okay, really cool. A quick follow-up question to that, and this is my question. Do you do any rotational or angular difference? And would that give you any data on, how the layers are oriented or anything like that, out of curiosity?
Yeah, so that kind of analysis we typically do using X-rays. As I said, we have a fairly smooth, flat film. So it kind of, we hit the ideal picture fairly well. Like what is the ideal sample for this transmittance measurement? So, and that's why our sample making takes sometimes years, because we want to hit that mark so that these characterizations become very smooth. But other than that, but there could be a situation where your question is relevant. We would want to make suppose a wedge-shaped film and then look at some specific aspects of that. But we haven't come to that point yet.
Okay, pretty cool. There's a question from the audience about missing the complete presentation. Thank you for that. But if you email myself, Dipanjan, or on the flyer, there should be contact information. We can send you the PowerPoint presentation and make ourselves available for any questions after the Q&A session as well. Another question from the audience is, it shows significant changes in bandgap appear to occur from single or low layers versus thicker layers. Does bonding between layers or non-uniformity and layer structure come into play?
Actually, that's a very good question. Absolutely, it does. Now, bonding between layers, that's actually one of the good things about it, that there is something happening what we call intrinsically to the material when you thin it down. So suppose if you have bulk material, right? So you have bonding in both X, Y, and Z direction. Now, when you make a single layer, of course, the bonding is only in the X, Y direction, in plane, right? So the out of plane bonding is non-existent. That is actually one of the reasons why this band gap changes dramatically. So that is an absolutely good point. But this is something intrinsic to the material, in the sense that, because the stability of the material comes in, and that determines what kind of bonding you will have. So that is absolutely a good point. Now, the non-uniformity in the layers is something that I guess we can control in a way. But if we have, like in our case, we were seeing highly disordered samples initially. It was not mainly that these samples are non-uniform in terms of thickness. They did have, chemically, they were imbalanced. So that, of course, makes a big difference. Now, if you have a chemically off stoichiometric, as we call it, material, then what happens, you do see a lot of metallic character. You see a big tail in your absorption spectrum. So, and that, honestly speaking, sometimes we don't like to see that, and we will not report it unless we have fixed it. So we spend a lot of time to make sure these chemical disorders are gone. And like we're showing, as soon as the sulfur was replenished, we see those nice exciton peaks. And, so yes, those are definitely very important factors. And some of it is good, some of it is bad, and we have to fix those things, yes.
All right. The next question from Venkata in the audience is the questions regarding particulate matter extracted in organic solvents like methanol. When you extract an organic solvent, do we need to consider reflectance, or is it straightforward absorbance?
Yeah, this one is straightforward absorbance. We are doing, sorry. Okay, sorry, I thought I was getting some feedback. So yeah, this one is straightforward absorbance because we are not dissolving. So this is a solid thin film. So the main interference is coming from the substrate. So what we do is we first do a reference substrate measurement, and that's why we have this two-beam spectrometer. So we put the substrate in one channel and the substrate plus film in another channel. So we correct the substrate. So we do not face any absorbed solvent issues here. But yeah, so the substrate turns out to be our biggest annoying factor as far as the films are concerned.
All right, cool deal. I had one more question myself. I was talking with Mark Talbot, who's he's part of our training department, but he used to be one of our Spectro product managers. And I was asking the question if pressure changes during the growth process of the crystals change the lattice structure, kind of like graphite and diamond. He did mention that PVD-CVD occurs at very low pressures. Do you do any change of pressures to change the lattice structure? Is that something that's done in the field, or is that a silly question?
No, not at all, actually. So the pressure studies, I did, in one of my earlier postdocs, I was looking at how pressure affects the optical properties of material. But here, when we do pressure, actually that's the reason, as you said, when you apply pressure, the lattice constants change. And once the lattice constants change, the electronic structure will change, and therefore the optical response will change. So absolutely direct correlation. But we do not, sometimes what we do in the film growth stage is that we can apply the substrate to apply what we call strain in the sample. But in a good or bad way, these particular materials do not respond to this substrate-induced strain a whole lot because they are so flaky. They always stay like they, in only one method. They don't like to get strained very easily. So that kind of doesn't work for this material, but for other material, yes, you can put a different substrate and change the lattice parameter of the film and then measure the optical response. And that becomes a whole, great research project on its own. But so now coming back, what do you do with these samples? Well, for these samples, you can apply a pressure externally. So there is a, like, I don't know if you guys have those accessories. There is, you can have a pressure anvil, and you have a small bore in the middle, and you send, you apply the pressure on the sample, and then you send the light through, so that, you know, it comes out transmittance. So there is a whole new research project that can happen by looking at pressure studies. So absolutely, yeah. I mean, there are, and the one of the reasons why that would be interesting is that, you know, when you change the lattice parameter, sometimes this material can change from a semiconductor to a metal sometimes. Or sometimes, you know, you can change this material from being semiconducting to a superconducting. So all these transitions can happen, and then, you know, you are in game. You can actually have a whole PhD thesis just on this topic, pressure-induced transformations, and you're doing optical transmittance, reflectance. And we also like to put other things like magnetic field. That is sometimes not really thought about, that why do you want to apply a magnetic field to a sample, but some materials are called magnetochromic. That means if you apply a magnetic field, the color of the material changes, and those magnetochromic materials becomes now very interesting for, like, you know, you're detecting color sensors and stuff like that. So yeah, there is a lot of exotic things, but you need some specific kind of material. Not every material will show all of these things. So yeah, you know, pressure studies, applying temperature, of course, is, everybody knows that. Applying magnetic field is another parameter. So lots of tools. Yeah, I was actually thinking about adding some of these. I think even Matt, I even talked to you once about having a fiber optics and then going to a magnetic field chamber that we have in our lab. So kind of, I'm not pursuing that right now, but maybe very soon we might do that.
Awesome. Thanks for such great answers. And I think we'll end the question session now since we're running out of time. I really want to thank you, all of Shimadzu, thanks you, and I'm sure all the listeners thank you. And I'll turn the floor over to you to say any last words, and after that we can end the presentation and Q&A session.
Sure. Yeah, thanks, Matt, for organizing. Thanks, Shimadzu, for this wonderful opportunity. This is the first time I'm doing a webinar, and I enjoyed the process. So if you have any questions, like, please feel free to ask Matt, or you can email me directly, and hopefully, you know, I'll be in touch with you guys.
All right. Well, thank you very much, and I hope everyone has a good day. Stay happy, healthy, and safe, and hopefully we get back to whatever normal is soon. So see you, everyone. Have a good afternoon.
Thanks, guys.